Okay. Today still section 1.7. Two topics. The first topic, I introduce linearly dependent set and linearly independent set, and then I present examples, more examples about these two concepts. Okay. Before I present these two topics, let me present some statistics about exam 1. I will post my solutions to exam 1 on wild course. Say today I post my solutions on wild course. About exam 1, let me see. The average is 85.43. So overall, our performance on this exam is good. Okay, it's good. The median, the student who is in the middle is 91. Very good. How many students whose scores are 90 or above? 90 or above. How many? 12 students. Okay. Okay. The top score is 99. So overall, exam 1, the whole class did a good job. Okay, now let me present these two topics. First, take a review about some key points from the last class. To study mathematics, definitions are important. Okay, when you do your homework problems, exams, remember the definitions. This is from the last class. If a vector is a linear combination of some other vectors. Linear combination, that means that you can find scalars C1, C2, and CK, so that this equation is true linear combination. If you can write vector V as a linear combination of these k vectors, then we say that vector V linearly depends on these k vectors. So linearly dependence is the same thing with linear combination. Otherwise, if you cannot find scalars so that this equation is true, or if vector V is not a linear combination of these k vectors, then in the case we say that vector V is linearly independent of these k vectors. This is the definition of a vector depends on the other vectors. Remember the definition. Okay, now topic 1. Linearly dependent set, linearly independent set. What that means? Definition. Okay, mathematics always definition. Topic 1. Okay. Definition. Okay. A. We have a set of vectors. A set of vectors. Say, this set, suppose, has k vectors. K vectors. Say, each vector is in Rn. Any example? Say, for example, 1, 2, 3, 4, 5, 6. 2 vectors in R3. In R3, 2 vectors in R3. So now suppose that we have k vectors. Suppose we have k vectors in Rn. Put these k vectors together, then we have a set. Okay, we say that this set is a linearly independent set. What it means is set to be a linearly independent set. What it means? The meaning is the following. If the following vector equation this vector equation x1 unknown times v1 plus x2 unknown v2 plus xk vk equals to 0. This vector equation is a linear system because the right hand side is 0. This linear system is homogeneous linear system. A homogeneous linear system always has at least one solution. The solution is 0, 0, 0, 0. But the solution, we call it a trivial solution. Non-zero solution is non-trivial solution. This vector equation always has at least one solution. The solution is 0, 0, 0, 0, 0. Right? If this vector equation has only the trivial solution, then we say that this set of k vectors is a linearly independent set. So when you want to answer a question, whether or not this given set is a linearly independent set, go to the definition, solve this equation to see whether or not this equation has non-zero solution. If no non-zero solution, then the set is independent set. Definition is here. Okay. Otherwise, if this vector equation has non-trivial solution, that means that non-zero solution. In that case, we say that this set is a dependent set. Otherwise, the set, this given set is a linearly dependent set. Okay. When you do your homework, always refer to the definition. Okay. This is A. B. When we say that K vectors, yeah, we are given K vectors. We say that these K vectors are linearly independent. What it means? We mean the set put these K vectors together, we have a set. This set is a linearly independent set. Similarly, when we say that these K vectors are linearly dependent, yeah, these K vectors are linearly dependent. We mean put them together, we have a set. The set is a linearly dependent set. Dependent set. Definition. Okay. Very important. Okay. Definition explains the meaning. Okay. Now take a look at examples about the definition. Okay. Example 1. Let be given some vectors V1, 1, -2, -4. V2, 4, -8, -16. These vectors are in R3. Uh, 0, 1, 1. Okay, all in R3. 4 vectors in R3. Now, questions. A. Determine if the set is linearly independent. To answer this question, go back to the definition. B. If possible, find a linear dependence relation among the vectors. Okay, 2 questions. Now, solution to question A. Determine if the given set is linearly independent. Go back to the definition. Definition says that we need to solve this equation. If this equation has non-zero solution, linearly dependent. Otherwise, linearly independent. Okay, now to answer the question, solve this equation. Is equal to 0. This vector equation is a linear system. It is a linear system with the augmented matrix. Augmented matrix, this matrix. First column, coefficients for the unknown, x1. Coefficient for the unknowns, x1 is vector v1. So 1, -2, -4, vector v1. Second column, coefficients of the unknown x2. It is vector v2. Vector v2 is here. The third column, vector v3. The fourth column is this. Then right-hand side, 0. Solve this linear system. If the linear system has only 0 solution, then the set is independent set, otherwise dependent. And now let me reduce the augmented matrix to epsilon form. I skip the details. This matrix is not just in epsilon form, but in reduced epsilon form. All right, now from the epsilon form, I can see that first column contains a pivot. So x1, basic variable. Second column contains no pivot entry. So x2, free. x3 also free variable. x4 basic. This linear system, because the right hand side is 0, it always has a solution. The linear system is consistent. Now the next question is how many solutions the linear system has? Infinite many solutions, because the linear system has 3 variables. So the linear system has infinitely many solutions. In other words, the linear system has non-zero solutions. Okay. Therefore, this vector equation has non-zero solutions. So, by definition, the given set is linearly dependent set. So, conclusion, V1, V2, V3, V4 is a linearly dependent set. by definition. Done. Finished. This is the answer to the first question. Now, second question. If possible, find a linear dependence relation among the vectors. What the second question means? Second question means find one particular solution to this vector equation. Okay. Now, reduced epsilon form is here. Now let me write the epsilon form in equations. Solution to B. Okay. In equations, the final augmented matrix in part A, the final augmented matrix in part A is this matrix. Now let me write this matrix in equations. Is the following linear system: x1 plus 4, x2, 3x3 is 0. Then x4 is 0. The third row here. This equation is 0 equals to 0. Yeah. The general solution of the linear system is solve for the basic variables. The basic variables is x1 and x4. Solve for the basic variables in terms of the free variables. From the first equation, I get this equation. Second equation, the equation is always be true. X2, x3, arbitrary. Yeah. This is all the solutions of the linear system. Now I want to find one particular solution. Let me choose. For example, x2 be 1, x3 be -1. Then I get one solution. The solution is plug-in 1 in x2, -1 in x3. Then I get x1 is -7. X2 is 1. Okay, here x2 is 1, so 1. X3 -1. How about x4? Always 0. One particular solution. Therefore, I can answer question B. Find a linear dependence relation among the 4 vectors. Plug in my solution in the vector equation here. Okay. Therefore, 1, because the linear system has infinitely many solutions, so there are infinitely many linear dependence relations. Okay, the following is just one dependence relation among the four vectors is, okay, negative 7 times V1 plus 1 times V2 plus negative 1 times V3. So minus V3. And then plus 0 times V4 is 0. Yeah. This is a dependence relation among the four vectors. So done. This is example 1. Let me make some remarks about this example. Okay, remarks here. Let me put remarks here. Remarks about example 1. Okay. From part A, the solution to part A is these vectors are linearly dependent, not independent. Okay. From part A, we know that these four vectors is linearly dependent. Yeah, the four vectors are linearly dependent. Okay, now go to this equation. Yeah, go to this equation. From this equation, let me move V2, V3, V4 to the right side. Then divide the equation by negative 7. Okay. Let me give a name to this equation. Say a star. From star, we have V1 is 1/7 V2 minus 1/7 V3, then plus 0 V4. Right? I move V2, V3, V4 to the right side, then divide the equation by negative 7. Then I get this equation. So this equation says that V1 is a linear combination of V2, V3, V4. By definition, V1 depends on V2, V3, V4. So by definition, so V1 linearly depends on V2, V3, V4. Again, from this equation start, if I move V1, V3, V4 to the right side, okay. Again, from equation start, we have V2 is equal to 7 V1 plus V3 plus 0 V4. V2 is a linear combination of V1, V3, V4. So by definition, V2 linearly depends on V1, V3, and V4. Similar, very similar. From start, if I move V1, V2, V4 to the right side, then I get this equation. V3 is this equation says that V3 linearly depends on V1, V2, V4. So this set is a linearly dependent set. From this example, we see that some vectors linearly depends on the other vectors. How about V4? How about V4? If I move V1, V2, V3 to the right side, but this time I cannot divide the equation by 0. So let me write on the last page. But from equation star, star means this equation. From equation star, we see V4 is not a linear combination of V1, V2, V3. Recall that the linear system has infinitely many solutions. Here, the solution is just one of the infinitely many solutions. If you can pick some other solution, here is non-zero, then I can write V4 as a linear combination of V1, V2, and V3. But unfortunately, in this example, X4 is always 0. That means that, yes, the linear system has infinitely many solutions, but X4 is always 0. That means that we cannot write V4 as a linear combination of V1, V2, and V3 in this example. Since X4 is always 0, no matter what particular solutions that you pick, the coefficient of V4 is always 0. That means that V4 always is not a linear combination of V1, V2, and V3. So the conclusion is V4 is linearly independent of V1, V2, V3. So the conclusion is, yes, this set is a linearly dependent set. In detail, we can say that this guy depends on the other 4 vectors. This guy depends on the other 3 vectors. This guy depends on the other 3 vectors. But V4 doesn't depend on the other 3 vectors. Yeah. This is example 1. Now, from this example, we have the following figure. Okay, figure. Okay, let me present the following figure. Motivated from this example. Okay, figure. Okay, let be given a set of vectors. S means set. Okay, the first letter of the word set. Okay, let S be a set of k vectors, be a set of at least two vectors, two or more vectors. All right, now conclusion. A, S this set is a linearly dependent set if and only if at least one vector, one of the vectors, at least one of the vectors, at least one of the vectors in S in the set is linearly dependent on the other vectors in the set. Okay. If this given set is a linearly dependent set, then at least one vector. Not all, not all, okay? At least one. Depends on the others. Okay, here. Pay attention here. At least one. I don't say that. I don't say all. Okay. I don't say all. Okay. B. S is a linearly independent set. Actually, part B follows from part A. Part B and part A, they are same thing, same thing. S is a linearly independent set. What it means? If and only if low vector in the set S linearly depends on the other vectors in S. In S. Yeah, part A and part B actually they are the same thing. Okay, part B follows from part A. From part A. S, the set is a linearly independent set. If and only if the vectors in the set are linearly independent to each other. This is a part B. Now, let me prove part A. Okay, proof of A. Okay. If and only if, so the proof has two directions. The first direction here. Suppose the set is linearly dependent set. Then I want to conclude that one of the vector is linearly dependent on the other vectors. Right. Suppose this direction. Suppose S is linearly dependent. What is the meaning of linearly dependent? Go back to the definition. Definition here. The set is linearly independent if this vector equation has only zero solution. If this vector equation has non-zero solution, then the set is a dependent set. Okay, now the set is a dependent set, so this vector equation has non-zero solution. This is definition. Suppose S is linearly dependent, then this vector equation has a non-trivial or non-zero, the same meaning, solution. Okay, say the solution is for example, C1, C2, CK. Okay. C1, C2, CK, at least one of the numbers is non-zero. Without loss of generality, we can suppose, right, C1, C2, CK, at least one is non-zero. Say suppose C1 non-zero. Then I can write V1 as a linear combination of the other vectors. Then, okay, C1, V1, C2, V2, CK, VK is zero. Okay, now I can move V2, V3, VK to the right side, then divide the equation by C1. Negative C2 over C1, V2, minus C3 over C1, C3, and so on, minus CK over C1, VK. This is a linear combination. This is a linear combination. By definition, when I can write a vector as a linear combination of other vectors, we say that the vector depends on the other vectors. So V1 linearly depends on the other vectors, V2, V3, and VK. So this direction, I have proved it. If a set is linearly dependent set, then at least one vector depends on the other vectors. I'm done this direction. Now, the reverse direction. This direction. Suppose one vector in S linearly depends on the other vectors in S. Okay, yeah, the reverse direction. At least one vector depends on the other vectors. Then I make conclusion. S is a linearly dependent set. Okay. 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 There are k vectors. I don't know which vector depends on the other vectors. without loss of generality. Without loss of generality. Suppose V1 linearly depends on V2, V3, Vk. Then V1 linearly depends on V2, V3, Vk. What it means? Go back to the definition. The definition says that the meaning is V1 is a linear combination of V2, V3, Vk. Then V1 is some scalar times V2 plus some scalar times V3 plus scalar times Vk. This is the meaning of linearly dependence of a vector on the other vectors. Okay, now from this equation, let me move everything on the right side to the left-hand side. Okay. Now move everything. Each thing is a vector. So I move everything to the left side. So the right side is only zero vector, not scalar. And this equation says that so one, okay, the coefficient of V1 is 1. Coefficient of V2 is -2, -3, -k is a non-zero solution because the first number is non-zero. Whenever one number is non-zero, then the solution is a non-zero solution. It's a non-zero solution of this vector equation. Okay, when this vector equation has a non-zero solution, go back to the definition. The given set is linearly dependent set. So the set S is a linearly dependent set by definition. This is very important. By definition. Done. The proof is done. So this theorem provides us some insight about dependent set and independent set. A set is dependent if and only if one vector, at least one vector, depends on the other vectors. A set is independent. That means no vector depends on the other vectors. When a set is independent, the vectors in the set are independent to each other. Good. This is topic 1. Second topic, let me see. Topic 1. I'm done. I introduce you the concept of linear dependent set, linearly independent set. And then I prove a very important feature. Now, second example. More examples. Topic 2, more examples about these two concepts. Let me show you more examples. Topic 2. Topic number 2. More examples. So that you can better understand, okay, the concepts. Example 1 under this topic. Consider this set. This set has a single vector, okay, of a single vector. Okay. Now, A, if vector V is a non-zero vector, then the set is a linearly independent set. Let me answer this question first. Solution. How to answer this question? Go back to the definition. Okay. The set is a linearly independent set. How to know that? Solve the vector equation. Yeah. Now only a single vector. So solve this vector equation. If the vector equation has non-zero solution, then the set is dependent set. Otherwise, independent. Okay. Because we non-zero. Because we non-zero. To make this equation true, x must be 0. No choice. Say for example, 1, 0, 1, 0, 0, 0. Non-zero vector times x is equal to 0. The solution is x is 0 because compare the first entry. The first entry on the left side is x. The right entry, the first entry on the right side is 0. So x is 0. Okay. This vector equation has only 0 solution. By definition, the set is independent set. So conclusion is S, this set is independent, linearly independent. Now B, if the vector is a 0 vector, then S is a linearly dependent set. How to answer this question? Definition. How to know the set S is a linear dependent set? Solve this vector equation. Now vector V is a 0 vector. This equation has infinitely many solutions. Say, for example, let me pick x is 1. This equation is true, right? So this equation has non-zero solution. By definition, S is a linear dependent set. By definition. Yeah, always definition. Example 1. Example 2. Example 2. So that the columns of the following matrix, for a matrix, each column is a vector. The columns are linearly dependent. Okay, the matrix is here. 1, 2, 3, 4, 7, 0, 1, 1, 9, 6, 9, 5, 8. Yeah, this matrix. Each column is a vector. Okay, now 4 columns, so 4 vectors. Together, put these 4 vectors together, we have a set of 4 vectors. Now, this set, so that this set of 4 vectors is a linearly dependent set. How to solve that? Definition. Okay, solve the following vector equation. X1 times first column, X2 times second column, X3 third column, X4 last column is right side 0, 0, 0. If this vector equation has non-zero solution, then the 4 columns are linearly dependent. Okay, but this vector equation is a linear system. It is a linear system. The augmented matrix is this. Okay, first column, coefficient of the unknown x1, 1, 7, 6. Second column, coefficient of x2. Third column, and then right hand side 0, 0, 0. So this linear system is a homogeneous linear system. Now solve this linear system. Let me see whether or not it has non-zero solution. Let me reduce the augmented matrix to epsilon form. Let me give a name to this matrix. Say, let me call it coefficient matrix A. Right hand side, of course, 0. Yeah, give a name. Yeah. Now, next page, I reduce this augmented matrix to epsilon form. Now, A, 0. Reduce to epsilon form. Zero, 0, negative 61 over 7, 143 over 14, then 0, epsilon form. From the epsilon form, I can tell whether there is a free variable. Okay. X1 first column contains a pivot. X1 the unknown basic. X2 basic. X3 basic. But X4 the fourth column contains no pivot number. So X4 is free. Now I can make conclusion. Since X4 is a free variable. Okay, go back to this vector equation. Let me give a name to this vector equation. Say double star. Okay, this vector equation double star. So double star has infinitely many solutions. So has non-zero solutions. Now, conclusion is the columns of the given matrix are linearly dependent by definition. So, conclusion, the columns of the given matrix are linearly dependent. Because the columns are linearly dependent, at least one column is linearly dependent on the other columns. In other words, at least one column is a linear combination of the other columns. Done. Done. Example 2. Now, more examples. Example 3. Example 3. If a set contains the zero vector, we have k vectors in a set. I don't know which one is a zero vector. Okay. Then the set S is a linearly dependent set. Whenever a set contains the zero vector, the set must be linearly dependent. Why? Okay. K vectors, I don't know which one is a zero vector. Without loss of generality. Okay, suppose VK is 0. Okay, suppose VK is 0. Now, let me write VK as a linear combination of V1, V2 to VK minus 1. Okay. Now, let me write VK. VK is 0. Okay, 0. Okay, now 0 actually is a linear combination of any vectors. I can write 0 as 0 scalar times V1. 0 scalar times V2. 0. Okay. So VK is a linear combination of V1, V2, Vk minus 1. When a vector is a linear combination of the other vectors, by definition, we say that the vector linearly depends on the other vectors. Okay. So Vk linearly depends on V1, V2, Vk minus 1 by theorem. Yeah, the previous theorem says that a given set, if one vector linearly depends on the other vectors, then the given set must be a linearly dependent set. So by definition, okay, S is a linearly dependent set. Yeah. So I prove done. Okay, done. The solution is done. Yeah. S is a linearly dependent set. Yes, yes, yes. Example 4. Example 4. Okay. Let S be a set of k vectors. Right? Be a set of vectors. Each vector is in hollow N. That means that each vector has n entries. A. If k, the number of vectors in a set greater than n, n is the number of entries in each vector. If number of vectors greater than the number of entries, then S must be a linearly dependent set. How to answer this question? Go back to the definition. Solve this vector equation. If the vector equation has non-zero solution, then the set is dependent set. Okay, but this equation actually is a linear system. Okay, which linear system on many pages is V1, V2, Vk, and then right hand side. Okay, yeah. This matrix, how many rows this matrix has? N rows. Okay, n rows. Now from here to here, k columns. Now k greater than n. This linear system is an underdetermined linear system. The number of equations less than the number of unknowns. So if you reduce the augmented matrix, you will see there must be at least one free variable. Okay. This system assumes k, the number of unknown, greater than the number of equations. The system has at least one free variable. Therefore, the system has, this equation has infinitely many solutions. Okay, this is a triple star. Therefore, triple star has non-zero solution. Okay, so when this vector equation has non-zero solution, the set is dependent set. S is a dependent set. So done. Done. Okay. This is a K. K, the number of vectors greater than the number of entries. How about the reverse case? Okay. B. If K less than or equal to n, then no conclusion on S. S can be dependent, can be independent. Say, for example, let me pick some example. Okay. Say, for example, 1, 0, 0. 2, 0, 0. Yeah. 2 vectors in R3. Now K is 2. K less than n. But these 2 vectors are linearly dependent. You agree? Because 2, 0, 0, I can write it as 2 times 1, 0, 0. So 2, 0, 0, this vector depends on the vector 1, 0, 0. So this set, dependent set. Okay, a second example, say, a second example here. 1, 0, 0. 0, 1, 0. Yeah. These 2 vectors is in R3. Now, K is 2. K less than 3. But this time, these 2 vectors are linearly independent to each other. How to see? Solve this equation. X1 times 1, 0, 0 plus X2 times 0, 1, 0 is 0. This vector equation has only 0 solution. 0, 0. Only X1 is 0, X2 is 0, make this equation true. So when this vector equation has only trivial solution, the set is linearly independent set. So these 2 vectors are linearly independent to each other. The first vector, you cannot write it as a linear combination of the second vector. The second vector cannot be written as a linear combination of the first vector. They are linearly independent to each other. So in this case, when the number of vectors not greater than the number of entries, no conclusion about whether the given set is linearly dependent. Okay, no conclusion. Okay. This is example 4. I finished today's class with this example.